about inverse functions and inverse relations. Today we need to add a notation to that. And we also have to begin to discuss domain and range. For when you have an inverse, sometimes there are restrictions on the original function, and then you have to make sure that those restrictions carry over when you look at the inverse. So yesterday we did a strict y equals something, and there was an x in it, so a y and an x, and we switched the y and x. Today we're using that function notation, f of x, if you remember. Okay, f of x. And then the way that you notate to have an inverse function is with a little -1 up the top, and that's f inverse is how you would say that one. So when you switch the x and the y, it's still easier to replace f of x with a y and switch those two things and get the y by itself. At the end, that new y would actually be f inverse of x. So we would have those things to consider. Okay. And as we're recording this, I'm just going to keep on going with this. So we're going to replace this with a y. And we're going to talk about our domain and our range here. So our domain, remember, is all the values that x is allowed to be. And the range is all the numbers that y is allowed to be. And so our domain here, since we're looking at the values that x is allowed to be, remember you can't have the square root of a negative and still have real numbers. So that means that x is allowed to be anything as long as x minus 2 is greater than or equal to 0, right? We can't have it be negative. So as long as x minus 2 is greater than or equal to 0, you need to write this down because it's most likely not something you're going to think about off the top of your head. So our domain is all the values of x so that x is greater than or equal to 2. Because if x becomes smaller than 2, we get a square root of a negative. That will put us in the imaginary zone, and that will mess up our idea of a function. And so, we have that. Can anybody talk about if this value, if this y has to be this, can anybody tell me about all of the possible y's that we might have, the range values? Like as long as this one, okay, if you're taking care of a positive, if you're taking a square root of a positive, what types of answers would you get? Positive or negative? Positive. You'd have to get all positive answers if you're taking square root of a positive, right? So that means our range, if we think of this as y, our range has to be all the numbers greater than or equal to 0. Okay, so as we think it through, the domain is all the x values. So x is greater than or equal to 2. And the range is all the y values so that it's greater than or equal to 0. So even though, I'll just hold that thought. All right. So we want to get back to figuring out what the inverse is. We can replace this with a y just like we did yesterday and then switch them so that the y will go under here and the x will come out here. Let me show you what I mean. So if this is the y equals square root of x minus 2, just changing our notation a little bit to more easily find our inverse. Switch your x and y like that. So you take your original, you switch your x and y, and you solve it. I would like everybody to be doing their best to keep up with the writing down. So even if you are somebody who's in the habit of not writing down, please write things down. Not a good habit to be in, just even if you're not getting it all and you're going to look back at the video later, it's still not a bad idea to write as much as you can and make sure you're understanding. So in order to solve for y, what do we need to do to both sides? Square it. We need to square it. We need to release this whole expression here. So we're going to square both sides. And when we square both sides, even though you don't see it here, but when we square both sides, we end up the square of a square root releases it from the radical, and then we have x squared over here. And then our last thing is to do what? Add 2 to both sides. Thank you very much. So we have y equals x squared plus 2, but our new notation tells us that that's the inverse of f. So we're going to change it over to that inverse notation. F inverse of x is x squared plus 2. Sure. We need to change it over to our inverse notation. We found the inverse by simply switching x and y. It makes it nice and easy to solve for y. But then this new y that we have is really the inverse function of the original, and our notation for inverse is with a little -1. Almost looks like an exponent, but it's our inverse notation. So our function is f of x equals square root of x minus 2. And our inverse, f inverse function is x squared plus 2. So we've got our brand new notation here. Same thing as yesterday. Switch your x and y. Solve for y, but at the end you have a new function called an inverse function. And what we need to do, we have our original domain and range, but then we need to talk about the domain and the range of the inverse function. What we notice here is that in this particular function, we're just picturing an entire parabola that goes moved up 2. But the thing is, for this one, is that actually half of it is going to be irrelevant because of the domain and range of the original function. The domain in the original function said that x had to be greater than or equal to 2. In our inverse function, our f inverse has to be greater than or equal to 2. Really, all we do is we switch our domain and range. So this is y is greater than or equal to 2, and this is x is greater than or equal to 0, and that's our finishing touch on our inverse function. So here it is saying again, okay, our inverse is this. Here's that note that I just said, just like x and y switched for the inverse, switch the domain and the range, which means the domain is now x is greater than or equal to 0. And our range is y is greater than or equal to 2. So when we're strictly talking about our inverse, we're only talking about half of the parabola. We could easily draw an entire parabola here, but we're actually only talking about the ones as long as x is greater than or equal to 0 and bringing that, just that piece of it. And if you have some graph paper, oh, never mind, not graphing this one. We could graph it if we wanted to, but we're going to leave home with that for right now. Just getting that idea of the domain and the range switch, in addition to finding the f inverse, getting our notation work out well. Good job. I'm just going to pause for a quick minute. So if we want to find the inverse, remember f of x is just a designation. You can use g of x or h of x. Usually f of x and g of x are the most popular of the function notations. But if we want to find the inverse and the domain and the range, what we can do here, think of this as a y equals. What I'd like you to do is I'd like you to actually put y equals 6 minus 4x. We want to consider what happens when we switch them. But first of all, let's think about the original. What's the domain and the range for this original function? Like, what's x allowed to be? Are there any restrictions on x? No, x can be anything. So x could be all real numbers. Well, look for things that x is not allowed to be. You're really kind of going backwards on this. Assume x can be anything. But then when you look at it, try to figure out what would possibly mess it up. Like, for example, if you have any square roots in it, you're not going to be able to stay in the real number system if you have a square root of a negative. So anything like that, you'd have to say has to be greater than or equal to 0. If you have any denominators or fractions that have a variable in the denominator, you'd say, well, that is not allowed to equal 0, and you would solve that part of the equation. So you might have an inequality saying greater than or equal to 0 or not equals to 0. Anything that makes it so that you have an impossible, incalculable thing would not be allowed. So this one, x is allowed to be anything. So x, the domain is all the real numbers. How about the range? When you plug just any random number in here, you're going to get an answer. Yeah, also any real number. Because you're not going to, you're always going to get an answer, and there's nothing really that it won't end up being, the positives, the negatives, and we can look at it like that. So our domain and our range for our original is all real numbers. And even for our inverse, if you switch them, we still get all real numbers and all real numbers, right? So before we even find our inverse, we know that our new domain and range for our inverse is all real numbers, all real numbers. So it might just be that you need to remember to answer the question and don't skip over that. But then switch your x and replace the g of x with y. And then what do? Replace it, switch. Do I bring the 4 with it? No, you don't bring the 4 with it. You just take the x out and you put a y there, and you put an x where the y was. So you're switching them, right? Looking right up there. The y comes out, replaces it with x, and here the x comes out and switches it with y. And now solve it. So I want you to take a minute. I want you to solve this for y, get y by itself. And we've got people doing that. Pause this for a second. So when you subtract 6 from both sides, we get x minus 6 equals negative 4y. Divide by negative 4. So you end up with negative 1/4 if you split it into the two fractions, negative 1/4 x. And then you have to also take negative 6/4. Be very careful not to just cancel out on one piece of the addition problem. This negative 4, remember, represents two fractions, x over negative 4, negative 6 over negative 4. So you would reduce those two, negative 1/4 x and 3/2 x. How would I write this in our good notation that we were talking about? Okay, good. So you described it correctly. We would say G inverse, but you described it very well as far as having the right, what it would look like. G inverse has that -1 that it looks like an exponent, even though it isn't, equals -1/4 x plus 3/2. So this is our inverse function. This is our original function. And if you were to graph them, we know that we have that dividing line, that line of symmetry that would go down on that. And for those that didn't see that, make sure that you watch. Yes.
How do you know that your domain is going to be and your instance on
Well, remember I said you can switch this one and this one. Since the domain is all real numbers here, the range becomes all real numbers here. And since, go ahead.
How do you know from the beginning that was last time?
For the domain?
Yeah.
Because there's nothing here that would provide a reason why you couldn't use a specific x. There's no square root, because a square root, you have to make sure you're always square rooting a positive. And there's no fraction here to provide a denominator that can't be a 0. So you've got those things. And since there's nothing that would cause a problem, then you have to assume that everything is allowed. Okay, so that's really what you're doing. You're kind of working backwards. Look for the problem numbers, and if there's nothing that causes that issue, then you can you don't have to worry about it. Okay, let's make sure everybody's still with us. And we can talk now about composition. Okay, remember we had the composition of functions that we talked about before with this little circle thing. It's not times. I'm going to cover it up in a second, but just so that we're thinking about that idea of the composition, so you can see it a little bit at a time. So f and f with the -1 here, this is f and f inverse. They're inverse functions. We just talked about how to find them. If you find, remember we did f of g of x and g of f of x. If we do the composition of f and its inverse, something special happens. Okay? You know how inverses, like adding undoes subtracting, and multiplying undoes dividing, and things like this, these inverses kind of work the same way. F inverse of f of x always just gives you x. No matter what the original function, no matter what the inverse comes out to be, as long as x is in the domain of f. So if you had a restriction, you might have a problem. But for the most part, you don't have to do any calculations or even know these functions in order to give the answer. So that would work. And also if you switch them, this is the only time that composition of functions actually comes out to be commutative, only when you have the function and its inverse. But once again, you've got to watch out for the domains. They might cause you a problem. Our thing that we want to be careful of. So for example, if we had f inverse of f of 5, the answer would be 5 without doing any work. If I had f inverse of f of 97, the answer would be 97. If I had f of f inverse of 23, the answer would be 23. Good. So it's always going to be giving that number back. But this little extra note, I need an example to actually explain that to you. So I want to go through this example. I want to do it kind of as rapidly as possible. We have just, it looks like a lot, but it is only just one more example here. So let's go through this. So let's say, for example, And what I might just do, because I really want you paying attention to this, I think I'll just run a copy. You can come by and see me later for this if you can't keep up as we go on this, because I want to be able to explain it all the way through. So I have my original f of x function as 1 over x minus 1. The domain x does not equal 1 because why? It would result in a 0 in the denominator. We can't have that. So y cannot equal 0 because there would be no way that you could divide one by anything that would end up giving you a 0. But we will see a little bit later how we can find that out and be a little bit better in the explanation. So we want to find our inverse. So you would put y equals x minus 1. You would switch the x's and y's. And then we'll use our algebra to go through and solve this. Now, as I said, it might be a good idea to go back over this, listen again at home. So we're going to solve for y. A thing you can do to get rid of this denominator would be multiply both sides by y minus 1. And when you do that, it ends up making the y minus 1 up here in the numerator. And then you can divide both sides by x to make these disappear, so you get y minus 1 equals 1 over x. And then we have our inverse function coming out as 1 over x plus 1. So in our inverse function, so this would be f inverse of x if we changed our notation. F inverse of x is 1 over x plus 1. Our domain is x does not equal 0 here, because in here, why can't x equal 0? Because, well, what if I made this into a 0? I have a problem because it's in the denominator, right? So you can't have a 0 in the denominator for the inverse function. So remember, our inverse function domain is the same as the range of the original. So even if you weren't seeing this y not equal 0 in the original, you can usually unravel it if you find the inverse and then make sure that whatever your domain is here becomes your range here. Whatever the domain was in the original becomes the range in your inverse. So you switch them in that way. Now let's get this example as far as our inverses here. Okay. Because I had said, okay, f of f inverse of 1. I'm showing you this the long way. We said our short answer is the answer is just 1, but I want you to see it happening. Okay, but the problem is that, yeah, we do have a problem there, but we'll just go ahead. So f of f inverse is 1. So we would plug that in to the f inverse function. And so we would end up with f of 2. We would plug that in, and you'd end up with 1 as an answer, and that's fine. You can avoid all this work if you just know the simple rule that f of f inverse of 1 equals 1. 1 is allowed to work because the only restriction in the domain of f inverse is that it can't be 0. So without doing any work, you could just skip all this and go right to f of f inverse of 1 equals 1. Now, when we look at this one, we have a problem. Because f of 1, if we try to do the f of 1 first, we end up with an undefined, and that gives you a no solution. Because 1 is not in the domain of f. So we have these things, and as I said, our shortcut is that f of f inverse of 1 is 1. And the f inverse of f of 1 is no solution because 1 is not in the domain. If you go back and check, 1 is not in the domain of the f function. And as I said, I would suggest going back and watching this a little slower since we ended up with the bell problem. So with this one, how much is f of f inverse of 5? 5. How much is f of f inverse of negative 27? Negative 27. How much is f of f inverse of 0? No solution. No solution. Hold up. No solution because we have, this is a restriction. This one, f inverse of f of 0 is 0 because the domain restriction for the original is that it can't be 1. And this one's just 85. So the shortcuts work for you. Have a very, very blessed day, everybody.